All right, we are going to start section 8.4 today. This is typically a pretty challenging topic for students in the past. This is the only section we're going to look at in chapter 8. And it deals with this idea of graphing what are called rational functions. And so I first just want to talk with you about what a rational function is, okay, so that you can easily identify these just by looking at an equation. Okay? So a rational function is an equation that has we'll say an x in the denominator. Okay? So a rational function is an equation that you notice there's a fraction, and then there's also a variable, an x, in the denominator. So let's take a look at what that equation might look like. If you look at the example down here at the bottom, you can see that in this example, it's clearly a fraction in example 1 here, and the denominator has a 2x squared minus 32. Okay? So this would classify as being a rational function. Okay? A rational function. You can also see on the back, as you look at each of these examples too, there are also x's in the denominator of those functions as well. Okay, just to give you a sense of how these equations, or graphs rather, look, these graphs tend to look rather odd. Okay? For example, you might notice when you look at a graph, and I'm just going to draw an example of a rational function here on the paper. You might notice that your graph is made up of a couple of different pieces. Okay? And then you might notice, you'll see these green dotted lines that I drew in the sample there. Those are called asymptotes. Okay? Asymptotes. And how asymptotes work, and we'll be looking at how to figure out where they're at here in a moment. As the graph gets closer to an asymptote, it won't ever touch it or cross it, but it will just kind of keep kind of riding it out. Okay, where it'll get closer and closer and closer and closer to it, but it won't touch it. And you kind of get the sense that that's what's happening with those two red sections of the graph that I drew there. So what we're going to try to do here is we're going to try to attempt to graph these rational graphs pretty much by hand. We'll use our calculator a little bit here, but it'll be very important. What you see in this blue box here, we want to make sure that we are comfortable identifying these aspects of a rational function. Okay, so we want to be able to say what the domain is. So let's talk about that part first, the domain of a rational function. I should tell you this, and this is really important for you to write this at the top. When we start these problems, you're always going to start by factoring the numerator and denominator. Okay? That's kind of your very first step. You always want to factor the numerator and the denominator. So if you could write that there, and then I'm just going to go ahead and highlight that so that kind of pops off the page there. Okay. So assuming we have done that first, let's go ahead and do that with this first example here. Okay, so I'm going to go ahead and scroll down to this example number 1. And I probably should have put here for step 1, I'm just going to abbreviate here, factor, numerator, and denominator. Okay, factor the numerator and the denominator. Okay, so we have spent some time talking about factoring. Okay, so we should be comfortable with how to factor both the numerator and denominator. Okay, so remember when we factor, we're always kind of checking for a GCF first. I don't see a GCF in this numerator. It looks like it's a trinomial with a lead coefficient of 1. So I'm going to go ahead and place 2 sets of parentheses, x at the beginning of each. I'll kind of think through an x puzzle here. I need 2 numbers that are going to multiply to be -2, but add to be +1. Those two numbers would be -2 and +1. So I will fill those in here, and now the numerator is factored. Looking at the denominator, I do see a GCF that we could remove from the denominator. So I'm first going to pull the 2 out, and then I want to examine what I have left behind here. It looks like this x squared minus 16, that we could factor that down. It looks like that's a difference of 2 squares. So I'm going to keep the GCF in front, but factor the x squared minus 16 into an x plus 4 and an x minus 4. Okay, and there we have the numerator and the denominator factored. Okay, so I'm going to go back up to this blue box right above here, and we're going to kind of look at each of these 4 elements: domain, vertical asymptotes, horizontal asymptotes, and then zeros of a function. You need to be able to identify those 4 things just by given the equation without really using your calculator in the graphical. Okay, so when we talk about the domain, here's the key thing that you want to be looking at with the domain. Okay? The domain is you simply taking only the denominator aspect to your equation, and you're going to set that denominator so that it is not equal to 0. Okay? And then you're going to take each of those factors, which we've already factored our denominator, and you're going to set each factor equal to 0, and that will tell you your exclusions. Because we know that when we work with fractions, we never want the denominator of a fraction to equal 0. So if we have variables in our denominator, we need to make sure that we're not allowing those x values that are in the denominator to ever be a number that would cause the denominator to be a 0. Okay? So this big capital D that you see on this bottom line here, that's for us to write the domain. Okay? So let's do the domain aspect of this first. Okay? There are technically 3 factors in our denominator, but only 2 of those factors have a variable in them. So I'm going to disregard the 2, and I'm only going to pay attention to the factors that have variables, so the x plus 4 and the x minus 4. Okay? So I'm going to set each of those factors equal to 0, and I'm going to say that the domain, I'm going to use my symbol here for all real numbers. X could be any number, except I do have 2 exclusions. I wouldn't want x to equal -4. I also would not want x to equal +4. In those 2 instances, that would cause the denominator to equal 0. Okay, and we don't want that. Okay? So that's how you find the domain and the domain restrictions for a rational function. Once you start out by having it factored, you only take the denominator and only the factors that have a variable in it. So maybe we should just make a small note here. When it says set each factor, it's just set each factor with an x equal to 0 to find the exclusions. Okay? All right, let's go ahead and look at vertical asymptotes next. Okay, vertical asymptotes have a really strong connection with your domain restrictions. Okay? You'll notice that a lot of these things talk about factoring. That's why it's important that your initial step is to factor the numerator and denominator. So your vertical asymptotes are going to also, like your domain restrictions, come from the denominator. So it mentions that you're going to factor your denominator, which we've already done, and then you're going to set each factor equal to 0. Sounds like the exact same thing we did when we found our domain restrictions. Okay? It actually mentions in the next sentence, any zeros of your denominator, these are also the exclusions of your domain, these are your vertical asymptotes. So we should just, again, make a small note here that when we say set each factor, we're talking about each factor with an x, any factors that would contain a variable. All right, so let's look down here. The VA line is short for vertical asymptote. Okay, I'm again looking at the denominator. I'm only concerned about the factors that have variables in them. I would set those equal to 0. Now, when you write the vertical asymptotes are these invisible vertical lines that run down through your graph. Okay? most of the time when you graph them on your calculator, the calculator isn't graphing the asymptote. It's only graphing the curves, okay? But you can tell the asymptote exists because you can tell that the section of the graph is kind of avoiding where that asymptote is, okay? So if you set each of these factors in the denominator equal to 0, you would discover that there is a vertical asymptote at both -4 and +4. And the reason I'm writing it as x equals is because those are representing vertical lines. So here's what I would definitely encourage you to do. Once you've found your vertical asymptote, I would like for you to place that vertical asymptote directly on your graph. And we're going to graph them as dotted vertical lines. Okay, so you're going to go to the x-axis at -4, and you're going to place a dotted vertical line at -4. And I want you to label either at the very top or you could label at the very bottom that is at x equals -4. So always label your asymptotes when you're drawing these on your paper. Then we're going to go to the x-axis where x is +4, and again, place a vertical asymptote there as well, okay, at x equals +4. Okay, so we know that this graph has two vertical asymptotes. The graph is somehow going to be in these different sections here, but it's not going to touch and it's not going to cross these vertical asymptotes that we have in place here. Okay, now let's go on and take a look at horizontal asymptotes. Okay, horizontal asymptotes, and if you recall, the example graph that I drew at the top here had both a vertical and a horizontal asymptote. Right here, there was a horizontal asymptote. I should mention, vertical asymptotes are a little bit more strict. They're very rigid, meaning your graph will never touch it or cross it. Horizontal asymptotes really more apply to the ends of the graph. The far left, the far right, the graph will never touch or cross the asymptote, although you will occasionally find graphs where in the middle of the graph, maybe somewhere around the origin, somewhere in the middle, it could pass over the horizontal asymptote. But it will never lay directly on top of it forever. It'll just cross over. Okay? Now, horizontal asymptotes are a little bit different from all the rest of these things that we're finding, because horizontal asymptotes, instead of having us look at the factored version, they want us to make sure that the numerator and denominator are put back in their non-factored form, which is what we would refer to as standard form. Okay? Oftentimes, this is how the original problem is presented, but sometimes they could give you the problem where it starts out already factored. Okay, what you're going to do is you're going to make sure that nothing is factored. So if you need to remultiply things back together, you would want to do that. Okay, and what you're going to be comparing when you're trying to find the horizontal asymptotes is you're going to be comparing the degree of your numerator, which I'm going to refer to as n, to the degree of your denominator, which I will refer to that as d. And you're going to use this chart below here. Okay? So remember, the degree of a function is always like the highest exponent for any given term. Okay? And so we're talking about comparing the degree of the numerator n to the degree of the denominator d. And essentially, you have three possibilities. Either n is greater than d, n is equal to d, or n is less than d. In the scenario where n is greater than d, you can see right across from that it says none. So that means if you had a problem, I'm just going to give an example here. Let's say that your equation was 2x cubed over, we'll just say 5x, okay? You can see that the degree of the numerator is 3, the degree of the denominator is 5. Clearly, the numerator degree is greater than the denominator degree. That is when I would say that there are no horizontal asymptotes. I'm going to jump down to the bottom row of this table, then we'll look at the middle one here. The bottom scenario is what if the degree of your numerator is less than the degree of the denominator. And sometimes you see it expressed even just like this, okay? Where even if you don't see an x in the numerator, the assumption is there was one there, but the exponent was a 0, and so that part dissolved out and turned into a 1. Okay, so this is an example where the numerator degree is actually less than the denominator degree. So for this, I would then conclude that there is a horizontal asymptote located at y equals 0, which is directly over top of the x-axis. My last scenario would be, what if the numerator and denominator degrees are exactly the same? So, for example, what if we had 2x cubed in the top, but then 5x cubed, let's say plus 1 in the bottom? Okay? You can see how both of these degrees are 3s, so they're equal. So here's what this is saying. If they're equal, you'll notice it says off to the side here, you're going to make an equation, y equals a over b. Now, a is the lead coefficient in the numerator, and b is the lead coefficient in the denominator. So in this example here that I created, the horizontal asymptote would run right through where y equals 2/5 on the y-axis there. Okay, so let's go ahead and apply this to this example that we're looking at here, the horizontal asymptotes. Now remember, we want to go back and we want to be looking at the original problem before we did any factoring. We want to compare the degree of the numerator to the degree of the denominator. So it looks like the degree of the numerator is 2, and the degree of the denominator is also 2. So that falls in our chart. You'll definitely want this notes page handy when you're working on this. At a certain point, you'll want to commit this chart to memory. But this is definitely falling in the middle row where they're equal to each other. So now I'm making an equation out of the lead coefficients, A divided by B. Looks like the A is a 1 and the B is a 2. So I'm going to have a horizontal asymptote at y equals 1/2. As you find these asymptotes, make sure that you always place them onto the graph itself. Okay, so this is good. Oops, I put that in the wrong spot there. Okay, it's supposed to be up at 1/2 here. All right, let's try. We're just going to eyeball this. Right across where y is 1/2. Always label. Okay, let's see here. Always label off to the side. I'll just throw a bunch of extra lines in there. That's positive 1/2. Okay. I'm going to try to clean up these extra lines that it just threw in there. Okay. All right, so we've got our horizontal asymptote and our 2 vertical asymptotes. The other blank that we just need to answer is what the zeros of the function are, and what the zeros of the function would be. Okay, so the zeros, again, are assuming that you have already factored your numerator and denominator. Okay? By the way, zeros is just another synonym for x-intercepts, like where this graph is going to cross the x-axis. The zeros occur if you factored the numerator and you set each factor equal to 0. Kind of like what we did with the domain restrictions, only we're doing it now with the numerator. Again, the assumption is you're setting each factor with an x. It's got to have a variable. If it's just a constant, it doesn't make sense to set that equal to 0. So let's look at the numerator for this. In the numerator, we had x minus 2 and x plus 1. So if we set those factors equal to 0, we would get that there is going to be an x-intercept at positive 2, 0, and another one at negative 1, 0. Okay, when you found those, go ahead and place those points on your graph. One at positive 2 and one at negative 1. We know the graph is going to cross the x-axis in those 2 spots. Once you have answered those blanks, we are going to rely a little bit here on our calculator to help us draw the curves in around the asymptotes. Okay? So you would go on your calculator, you're going to press y equals, and what we're going to be typing in, I would encourage you to type in the original problem before you factored it. Okay, so I'm going to go ahead and pull up the calculator here. Okay, and we're going to go ahead and type in x squared minus x minus 2. Oh, I should enclose that numerator in parentheses. Otherwise, I don't believe my calculator is going to realize that all three of those terms are in the numerator. So it's that trinomial divided by, again, you would want to use parentheses for the denominator. So, whoops, didn't take, minus 32. All right, I'm going to go ahead and just hit zoom 6, see what this looks like in a regular window. And you can see on my calculator screen, it's not drawing in the asymptotes, but you certainly get the idea that there's something there that the graph is kind of avoiding. So you're just going to use your calculator screen, and you're going to do the best you can with trying to sketch in around the asymptotes where the graph would fall. It looks like maybe, oh brother, sorry. Okay, let's try this again here. Looks like maybe we could draw one right here. And we know it's going to come up and cross those points and then come back down there, and then another one over there. Okay, that would be good enough. Okay. All right, let's go ahead and look at another one. Now that we've kind of been through one, let's go ahead and try another one here. We can hopefully do this one a little bit faster. Okay. All right, so we know that our initial step is to always factor. Okay, so we're going to go ahead and factor this trinomial with a lead coefficient of 1. Looks like the denominator, there's nothing that we could factor there, not even a GCF. I need two numbers that multiply to be -6, but add to be -1. Those two numbers would be -3 and +2. Now that we have that, we should be able to kind of zip through here. Keep in mind your vertical asymptote and your domain, you're looking at the same aspect of the problem. So domain restrictions and vertical asymptotes, those come from the denominator. Okay, those come from the denominator. So I'm going to write down all real numbers except x cannot equal -1, and my vertical asymptote is where x equals -1. So I'm going to come over to my graph. I'm going to go ahead and place a vertical asymptote on the graph at x equals -1, and I've checked off my domain and my vertical asymptote. I would encourage you to do both of those at the same time since they're very, very similar. Okay, I'm going to also go ahead and do the zeros, the x-intercept, because it's the zeros, the vertical asymptote, and the domain that you're looking at the problem in its factored state, okay? Except with zeros, you look at the numerator. Okay, you look at the numerator for that. So I'm going to go ahead and look at my factored problem, looking at the numerator. I have two factors there that have x's in them. So I'm going to go ahead and write down that I would have two x-intercepts, one at 3, so I'm going to put that point on the graph, and another one at -2. Okay, now all I'm left with is my horizontal asymptote. And you might need to flip back to the front of your notes page to look at the chart. We want to revert back to the original problem before it's been factored. Okay, so this is what we would be looking at here. We want to pay attention to what our degree of the numerator is and the degree of the denominator. I'm going to note that the degree of the numerator is 2. The degree of the denominator is 1. This is certainly falling in the section of that chart where the degree of the numerator is greater than the degree of the denominator. So I'm just not going to have any horizontal asymptotes for this particular graph. Okay, once all the asymptotes and the zeros are placed on your graph and you've answered all the blanks, you're now just going to go to the calculator and you're going to type the original problem into the calculator again, putting all the numerator in one set of parentheses, and then dividing that by the denominator all in one set of parentheses. Okay, I'm going to hit graph. Okay, I definitely am seeing how it's kind of skewing away from that vertical asymptote. I can see here that there are two x-intercepts Looks like it's at the 3 and the -2. So I'm going to go ahead and do the best I can here with just trying to sketch that in. You know, when it comes to this step and you're just sketching it, just do the best you can. You know, just look at your screen. You want to make sure you definitely are running it through those x-intercepts. So, okay, I want to just look at one last one here with you. Just make sure that we are comfortable with this process. It's just going to take a little bit of practice here for us to kind of get the hang of this here. So let's go ahead and look at this one. I think number 4, the final one, is already done for you. Okay, so I'm going to go ahead and factor yet again a trinomial with a lead coefficient of 1. Looks like we need two numbers that multiply to be -15, but add to be +2. Those two numbers would be +5 and -3. You can see any factoring problem thrown at you now. We've been talking about a lot of them here lately. So you can see that in this denominator, while there is no GCF that you could remove, and it is not a difference of two squares, we in the last month here learned about a sum of two cubes. If you recall, that's when factored, you can have a binomial followed by a trinomial. We had the acronym SOAP that we used to help us with our signs. We said if you're dealing with a sum of two cubes, then your binomial should have the same sign as that. The O in SOAP is opposite, and the AP is that it ends with always being positive. We then take the cubic root of our first term. We had always called that A. We take the cubic root of the second term. We had called that B. We fill in the A value and then the B value in the binomial. In the trinomial, we put the A value squared in front, the B value squared in back, and A and B multiplied together in the middle. Okay. Please remember this trinomial piece right there, after you factored a sum or difference of two cubes, you will not be able to factor that any further. So that means that that will not produce any more zeros. No domain restrictions will come from that. No vertical asymptotes will come from that. Okay, so now I'm ready to start. And I'm going to start with the domain at the bottom. I'm going to put a real number symbol. Okay, and then I'm going to put my exclusion. But the only exclusion is going to be from that binomial. X cannot be -2. The trinomial isn't going to produce anything. Okay, I've got a vertical asymptote at x equals -2. So I'm going to go ahead and place that. Again, notice when you place these on the graph, always label their location. Okay, now I'm going to move to the x-intercepts. That's when I'm looking at the numerator. I've got two factors in the numerator, both that have variables in them. So I'm going to set those equal to 0. I'm going to plot those points directly on the graph. Okay, and now I'm just left with my horizontal asymptotes. Okay. I want to see here, it looks like my numerator degree is 2. My denominator degree is, oh my goodness, that's really making a mess there, isn't it? Let's try to clean that up. I'm sorry. All right, numerator degree is 2. Denominator degree is 3. This lands me in the chart where the numerator degree is less than the denominator degree, which is when I would have a horizontal asymptote at y equals 0. Again, label that. Okay, all we're left with now is just reverting back to the calculator. We're going to make sure that we type that original function into the calculator. Plus 2x minus 15 over x cubed plus 8. Okay, I think I got that in right. We're going to graph. Okay, this has like a weird little hiccup in the graph. Okay, that's just how the graph looks. Oh, brother. All right, and we're just going to do the best that we can with trying to sketch that graph there. It would roughly, look something probably like this. I'll try to simulate that little hiccup. And here's a case where I was saying that the graph actually does pass over this horizontal asymptote, but it only does it kind of in the middle section of the graph. Okay, so horizontal asymptotes are a little bit more lenient than vertical asymptotes. Okay, that brings this section here, or this particular video, to a close. Just do the best you can on those problems on worksheet 8.4a, and we'll reconvene on the next video.